Assalamu alaikum everyone. I'm Faiza from Lahore. I completed my bachelor's and master's both in the field of mechatronics and control engineering from UT Lahore, and now I'm serving as lecturer in University of Management and Technology Lahore. Today I'm going to present my research work in the field of establishment, command and functional assay of artificial elbow. Let me share my file with you. The outline covers introduction, literature review, elbow anatomy and physiology, features of electromyography, design, implementation, working, and lastly, results. In the introduction, I would like to tell you about some basic terminology, which includes, first of all, bionics. In bionics, living systems are studied, the systems which are relevant to brain functions to use their working principles in developing engineering systems like these. Then we have bionic potentials, which are actually the ionic voltages produced by certain classes of cells due to their electrochemical activity. Thirdly, there is prosthesis, which is an artificial extension that is designed basically to possibly replace a missing body part with proper functioning. Moving on, next is the different types of artificial arms, which first of all has myoelectric dynamic arm, in which the muscle contraction in the residual limb gives electromyographic signal, which is then further used. Secondly, I have Luke arm. This prosthesis is controlled by body movements. The movements of shoulder or upper arm are captured by a harness system that will pull the cable attached to the prosthetic part, as you can watch in the diagram. Thirdly, we have modular prosthetic limb. The modular prosthetic limb control contains a microarray that is surgically implanted in the human body and will capture the action potentials directly from the motor points. Fourthly, we have targeted muscle reinnervation. This technique involves actually taking the nerves from a remnant of an amputated arm and then connecting it to another body muscle, that is usually the chest muscle. Number five, we have passive or cosmetic restoration, which is just a mask, which is merely a mask to amputation with no active working. Moving on with the literature view, I'm going to present a few papers. Firstly, there is non-back drivable series elastic actuators for prosthetic elbow. Usually, commercially available prosthetic elbows have one-dimensional motion just through stiff actuators. In this research, a less stiff motor is non-back drivable and is capable to be used in prosthetics as it is power preserving. Authors recommend to use series elastic actuators to provide advantages like high fidelity, flexibility, reliable force output, then design robustness, stable torque control, and less damage in the case of inadvertent contact. Second paper directs to a new approach in prosthetic elbow design. Electromyographic elbows can easily replace the passive ones if they possess the features like comfort, durability, lighter in weight, less power consumption, user friendly, and natural movement control, which is the most important one. In order to accomplish all these features, a design of linkages series were used which allowed good mechanical efficiency and low angular velocity of elbow. For efficient transmission, links would have low momentum of inertia. Thirdly, there is pro-dated steam prosthesis for partial hand absence. This paper provided information about partial hand prosthesis that had been developed by Touch Bionics, which is a British company. This device had free individual movements of fingers and was built into a socket to accommodate remaining hand portion. The purpose of this device was to provide amputees with normal grasping activities of life with either congenital or acquired with one or more finger loss. Moving on, I have problem statement then. which states the designing of a bionic elbow joint for the flexion and extension movement of elbow joint using EMG signal, which is the electromyographic signal. Methodology involves, first of all, signal acquisition through electrodes and differential amplification. Then after processing, this signal would be sent to microcontroller. The next stage is of signal interface with computer system, which then sends signal for artificial limb actuation ultimately. Prior moving on, I would like to discuss fundamental elbow anatomy and physiology that would help you to understand my research. In the anatomy, basically three main bones, namely radius, ulna, and humerus, meet each other in the center of arm and form elbow joint. In the physiology, elbow normally serves for two functions. Number one is the supination and pronation, which is actually the rotation of forearm up and down. And secondly, it is flexion and extension, which is the bending and straightening of the forearm. Electromyographic signal is the development, detection, and then recording of action potentials of skeletal muscle fibers. These small currents are actually the muscle fibers' response to nervous stimulation. During nervous stimulation, muscle fibers contract, and because of the ions exchange across muscle fibers membrane, owing to which small currents are produced. This EMG signal is quite random in nature, and even its voltage varies from microvolt to millivolt in range. The usable energy lies in the frequency band of 0 to 500 hertz. Detection and recording of the EMG signal depends on the properties of electrodes and their interface with the skin, muscle tissues, and further electrical components used within the circuit. Normally, the action potentials are detected non-invasively with electrodes placed on the skin surface of the muscle. Thus, the action potentials travel through the muscle fibers during muscle contraction and are then picked up by the electrodes on the skin surface. Moving on, the differential amplifier now show how the common noise signal is rejected that is present at an equal amplitude at each active terminal, and then gives the resultant EMG signal. Further, we have to deal with differential amplification and signal processing. For further amplification and processing, AD620AN amplifier and OP07 is used, which is a first order high pass filter. Here are the measured values for EMG signal across each electronic component in the hardware in the elbow's flexed posture. You can watch here that signal was initially negatively in millivolts on both electrodes, and later on it came out to be positively 1.5 volt. After processing, this signal is then sent to microcontroller. During the programming, an average EMG signal was stored, its average value was stored, and the elbow was placed initially in extended position. If the newly coming EMG signal value is less than this average value, the elbow will remain extended, and if it is greater than the average value, the elbow joint will perform then flexion. Next, we have circuit design. Its circuit design was like this, and for the purpose of computer interface, Advantic USB 4704 data acquisition module is used. It is a multifunctional module used particularly for EMG signal analysis on computer screen. As you can watch the different EMG signal curves on different electric components which are used in our circuit: electrodes, our amplifier, filter, and then microcontroller. Here is the prototype design of our project for this research work. In the mechanical hardware, worm gear DC motor is used, which is generally a high torque and low speed to support heavy load. Likely, next one is showing you the prototype pictures in the postures of elbow extension and flexion. With the help of DC warm gear motor, the joint is made to rotate to develop elbow flexion and extension movements based on EMG signal. Now I will show you the working of my prototype. The elbow joint works like this depending upon the signal received from microcontroller. So this is all about my research work. Thank you so much for your time.